I'm coming today, and then I had to tally up the rest.
All right, you tallied up. I trust you.
Okay. Thank you.
Okay, so welcome back, folks. Let's continue with our beautiful, handy-dandy buffer equation. So, I got a knock on my door. Come on in. You slipper folks, please come in. We'll start right up front because I've got some students not here today. Thank you for joining me. Okay, Daniel, I got, who else I got here? I got. Okay, welcome. Glad you could join us. So, Schnupper folks, we're right in the middle of a discussion of buffers. Buffers are chemicals that keep a system so they have the same pH. So it keeps your pH constant, whether it's something used in your blood, on your skin, in your hair. We're going to see how to do a buffer system right now. And these are two reactions. This one's given on the AP. We looked it up after some of you had already left, AP students. And this one is one that I always remember. Don't ask me why I have a harder time remembering this one, but one or the other is helpful for you. Probably the second one's more helpful because you have pH directly, which is what they often ask for in the buffer problems. Okay, so let's do it. Okay, I'm going to try and pick and choose carefully. No, I think I need to do the first one with you. This is similar to one, folks, in AP that we did and made together last time. So here's a little example. A buffer is made by dissolving moles of lactic acid and the Ka for that is 1.4 times 10⁻⁴ and 1 mole sodium lactate. Okay, lactic acid sport, folks. Where do we find that sometimes? Lactic acid, Nordeep?
I would say in our muscles.
In our muscles, especially it builds up if you do a lot of activity. That's why your muscles get painful. Sometimes the lactic acid's building up. But it can also be used to make a buffer. To make 550 milliliters of solution. Find the pH. Okay, so here's the deal. I want my AP students to be able to do this quickly. So if they want pH, let's just write the equation down and see if we can fit everything in to where we want it, and we've got it. Okay, so here we go. So they want pH. Let's just use that version. So the pKa plus the log of this fraction, the concentration of B minus. Well, let's not call it B minus. Let's not call it what it is. So it's lactic acid and sodium lactate. You don't know the formula, right, AP folks? You don't need it. Here's the beautiful thing. Let's just call it, let's do the bottom first. Instead of HB, how about we call it H-lac? Just make up a name. H-lac, why not, for lactose or lactic acid? And the top, we'll just call it lac with what charge? Minus, good, because it lacks an H plus. Get it? So there you go. So let's put stuff in. So the pKa is, find me the number. There it is, right?
Isn't that the K?
Yeah, so need the K. Oh, the pKa. So what do we do? Who remembers to get, that's the Ka. So what operation mathematically do we get to get the pKa? Can you recall? So like pH? We have to do? Oh, the.
Maybe negative log of,
Uh-huh.
would it be the Ka? or
Yeah,
would it be-
negative log of the Ka. So just like we got the pH by getting the negative log of the H plus concentration, the pKa is the negative log of the Ka. And I know, Snooper people, this is not something you're understanding, but I have to go through it at this point. With these folks, okay, plus the log of this fraction. Okay, so do I have these concentrations?
No.
No. How can I get them? What can I do, Aaron?
Well, you have the number of moles and you have your amount of liquid. And
You
then
do it. So I could divide moles by
the
liters, right? But you know what? It's even easier. Ready? Let's look at something we wrote right before the bell rang. Look at number 2 and tell me how we're going to make our life really easy here. Aaron sees it already. Let's hear everybody else. What do we do here with number 2? No V? Yeah, it's a 1-to-1 ratio. What don't I have to worry about here, Noah? I don't need the concentration, and I don't even need the 550 milliliters. If you think about it, if I divide both of them by 550, it cancels out anyway, right? Because they're in the same container. You know what I'm saying, folks? So it's just the ratio of their moles, which beautifully is just what ratio? 1 mole over 1 mole. I'll add mole just to make it nice. Isn't that lovely? So could you do that with me, AP folks? Take the log of 1 and then add it to the negative log of this 1.4 times blah, 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 blah. And let's see what we get here for the pH. So punch it out and we'll see if we get the same thing.
the log of 1 is 4.
The log of 1 is 0. Ah, how beautiful it is. So guess what? All you need is the negative log of the Ka. Isn't that cool? You think they'd ever put something like that on a multiple choice question? Absolutely. If they have a 1-to-1 ratio and you guys are good enough at math to know the log of 1 over 1 is 0, that's a beautiful thing because all they're going to do is give you an easy number for the Ka. We'll do one like that in a second. Okay, so punch it out. Let me know what you got. Lena?
3.9.
Sounds good. Others get the same thing? You got it. Is it an acidic or a basic buffer? Acidic or a basic buffer based on that number, Shilpa? It's acidic because it's below 7. Schnupper people probably know that as well about pH, right? Below 7 is acidic stuff. So it's an acidic buffer. Use. Okay, so jump to the AP test. Ready? Let's see if you can do this without a calculator. Yes, I made up the names. I made it up for Quinn. Let's hope he appreciates the humor. There you go, Quinn. You weren't here to make something so absurd, so I decided to do it for you. Here we go. So I got 1 mole of quacky acid. Let's say the Ka is 1 times 10 to the negative 6. And 1 mole of sodium quacky, sodium quacky. Well, to make a buffer, and its pH is, okay, again, use the handy dandy buffer equation. pH equals the negative log of the Ka plus the log of this ratio, right? So now we got crack minus over H crack. And no snooker people, I haven't lost my mind. I do this all the time.
Quinn says it's like you drag your finger across a keyboard.
Is that what crack is?
Yeah.
Thank you. I take that as a compliment, Quinn. Thank you. Okay, so pH is the negative log of, and I'm hoping, AP folks, you're just seeing me run through the thing. I bet everybody knows what the answer is going to be already. I hope so. Plus log of 1 over 1. Okay. Without calculators, tell me what the answer is. Good. 2 people see it. Let's let the others read through it and let their gears turn. 3 people see it. So the pH will just be what? Hint, the front number is 1. Front number is 1. Okay, Shilpa, you're on.
6.
6. Okay, what'd you do, Shilpa?
Negative log of that number, you just do the exponent, the positive is negative, so that'll be 6, and then log of 1 is 0.
Thank you very much. That's exactly right. Remember, we did this with pH. I know we didn't have this part, but we did negative log, and if the front number is 1, it's really nice. It's just the opposite of the power. And so it's just 6. So a slightly acidic buffer system with quacky, sodium quacky, and cracky acid. Okay, enough nonsense. You get the idea? Okay, so.
We can use one of the 2 formulas at the top on the top.
Yeah, and this is the one that I think, Sarah, you looked it up and found it, right? This is the one Sarah found that they actually give us, at least last year. We can check the website, but that was given information last year for the AP test. So in other words, you don't have to memorize it. It's given to you. Good. Other questions from you? Okay, let's do one other thing, and then we're going to leave buffers. Picking a buffer. So, hey, what do you notice? Because most buffers are 1-to-1, yeah, the pH of a buffer is usually close to the what? The pH of the buffer is actually, it's identical if it's 1-to-1. It's just equal to the Lena? No, it's not. What's up in our formula? Just read the formula, Tom. The pKa. Check that out. If this is 0, it's just the negative log of the Ka, the pKa. That's going to be some sort of question on your AP test, either multiple choice or some part of a FRQ. So the pH of a buffer is close to or equal to, if it's a 1-to-1 ratio. So close to or equal to the pKa of the acid in the buffer, or weak acid. That, if you think about it, is a beautiful thing. So anytime you guys want to build a system, a buffer system for any product, medicine, whatever, all you got to do is look up the table of KAs and then calculate out the pKas by taking the negative log. So, for example, in our book, I'm going to just give you that reference because it's kind of a powerful tool. And the pKas, I know they're at the front, but I think they're at the back too. Let me just take a quick gander. There they are. Page 567. Let's pick one for grins. You ready? So if you got your book with you, turn to page 567 for just a sec. That's the page with all the KAs. And how about I want a buffer that has a pH of about 3.5. Can you guys find me one by taking the negative log of a couple of them there? So let me repeat that and write it, and you're going to need your calculator for this. 3.5. Give me a system to use. So question is, what system, what acid, what weak acid / conjugate base to use? There may be more than one choice, but let's see if you can find one fairly close. Okay, so calculate out some logs of these guys and then take the opposite to get the negative log. And I know Schnupper people, you don't have this data, so it's going to be hard for you.
What's relatively close?
Well, how close did you get, Sue?
3.1.
That's a little far off. Can you do, is there one above or below that that's a little closer of the systems? I mean, that's getting close, but any of the others, Shopa?
I just had a question. Could you just plug it into the equation and then find the exact value?
Yeah, but I'm asking about what chemical to use. So here's a page of chemicals. Let's say you have those in your lab. Which set of chemicals could I use? And the answer is I could use several different ones. Like I can take the one Sarah gave me, whatever it was, and get 3.1 and adjust it to make a ratio to get exactly the pH I want. But it's easier if I get one where the pKa is pretty close to 3.5. Lena, you got one that's fairly close?
Yeah, I have 3.46.
Oh, dynamite. Which thing was it?
Hydrofluoric.
Okay, everybody look at hydrofluoric. So do what Lena did. Take the negative log of 3.5 times 10 negative fourth. And you got, what'd you get, Lena? You got 3.46, which is essentially 3.5.